Welcome back to Chapter 10, Part 2, where we are going to focus on the world of smog and where it comes from and how it happens and is it good for us, is it bad for us, is there anything that we can do to mitigate it, for example. And spoiler alert, it's not good for us. So I just brought this photo back up again. This is from last time as well. This is the difference between before and after the quarantine from coronavirus in Delhi in India. And what we're seeing on the left here is smog. This is typical smog. Hazy, brown, particulate matter and chemicals in the air. And then with people staying home, not using their cars, we see this. So this is part of the key ideas number 2 and 3 that we're going to get through today in this lecture. We're going to talk about photochemical smog and also acid deposition and how they're formed and the effects, and then also look at a few approaches to controlling and preventing air pollution. So, and this isn't just something that happens in big cities overseas or just in developing countries or even just in big cities in general. This can happen everywhere. And it's still a big problem in the United States. So we're going to start here with how smog forms before we get into acid deposition. And before we talk about the United States, good history lesson. Back in 1952 in London, there was this thing kind of referred to as the Great London Smog or the Great Smog that over a period of, I forget, maybe 4 or 5 days. It wasn't that long, but it was brutal time that this really heavy, dense fog set into the city of London. And there's estimates, some say 4,000, 8,000, between 4 to 12,000 people died from the smog. And it's just from the air pollutants. So you can read a lot about this stuff. I pulled this from an article from The Verge. And what happened is it basically spurred their national Clean Air Act, which was pretty unprecedented in the world, and it had a big effect on other world populations as well. There's basically notes here a blueprint for other nations to follow. So subsidies for people so it can begin converting coal burning fireplaces to smokeless fuel, which back then was very expensive. Um, they replaced restrictive rules on the industry. So this spurred a huge, huge force in legislature because of how many people that had died. I pulled up some photos from that back then. This is November 5th, 1952, and this is December 8th. Oh, I'm sorry. It was not over a period of 5 days. I think it was over a period of a month or two, a few months. I'd have to look up the time frame. I forget how long the Great Fog lasted. But either way, they were dealing with this really intense fog that came over the city. This was more so fog from coal. So burning coal back then from their power plants produced a lot of particulate matter. And that mixed with normal fog, that's really where this comes from. Smoke and fog, the word fog comes from, sorry, smoke and fog produces the word smog, a portmanteau of those two words. And another view, oh, yeah, so this is London. So a really big deal in London. So how did that spur the Clean Air Act in the rest of the world? Well, before we had any guidelines, for example, this is 1949, 1950 in Los Angeles, United States. And depending on the day and the air conditions, you get these smog events where it settles in the city and you don't have a lot of wind and you have this dense, thick, polluting air. And we see some, you can barely even see buildings sometimes back then in 1949. We still have problems in Los Angeles today, but thankfully there are a lot more guidelines that try to keep smog pollution down. But it's still pretty interesting to see how bad it was in the United States too back then. This is a more recent example. This is nothing to do with the coronavirus. This was in 2019, November 4th, in New Delhi Bureau. This is a CNN article. So this is a view from their building on 2 different days. So this is August 8th and then November 4th. So there can be drastically just different conditions on any given day depending on weather patterns. But this is a huge problem, and Delhi has a lot of air pollution. They're kind of well known for that. So how do we form the smog? Back then this was mostly coal, but now we don't burn as much coal as we used to. However, we still produce a lot of stuff that gets into the atmosphere. So smog really forms when sunlight reacts with things. Sunlight has a lot of energy. And when things get into the atmosphere that really shouldn't be there, things like nitrogen oxides and also volatile organic compounds, sun can react with them. And VOCs, volatile organic compounds, that's a broad classification of compounds, but you can think of things like gasoline, cleaning agents, solvents, paints, things like that. Stuff that people use on a daily basis that if they're not contained, they will evaporate and go into the atmosphere, especially gasoline is a common one. Think of every time you go to the gas station, so thousands of people every day spilling a little bit of gasoline on the ground, and that can go up into the atmosphere. So cumulatively, it's a lot. So these are, again, primary pollutants, nitrogen oxides from some natural sources, but a lot of that comes from our combustion processes. And then a lot of these VOCs are certainly not natural sources, but these are the primary ones that get into the sky. So the secondary pollutants, two that we're going to talk about, one is ozone, is a major component of this photochemical smog. So photochemical, as in light reacting with chemicals to produce a new type of smog. And sulfur is the main ingredient in sulfurous smog. So chemically, and kind of a picture, how does this act, how does this work? So let's look at this top one first. So this is pointing out NO2 from natural and anthropogenic human sources. Arrows indicating a reaction is occurring. So sunlight is helping this break down into these high energy species. Oxygen we typically see as O2 bonded together. But if it breaks down, this is a very reactive species. So what can happen is this can react with another molecule of just monoatomic oxygen and produce more oxygen. That can happen. That's fine. However, NO is now another very reactive species. But if this O2 from the atmosphere reacts with a molecule of this, instead of just going back to dimolecular oxygen in the left direction, it actually forms O3, and that's ozone. This is a very reactive species. So again, we're breaking down NO or NO2 into these pretty reactive species, and then this reacts with another molecule of O because two molecules of this can break down, and all of a sudden, oh, I'm sorry, this reacts with another molecule of O2, excuse me, to produce O3. So we have this secondary pollutant ozone, which again is very reactive. It's not good for us. It's it can get into our lungs. It can cause reactions. When you talk about ozone, we have this ozone layer in our atmosphere. That is true. That's a very high, that's way up in the sky. That's actually helpful. That helps keep harmful UV radiation out of our environment. But this is happening close to us. So this is happening just, above our cities. This can actually get down and hurt us. This other example is showing NO2 again, breaking down into nitrogen monoxide in another molecule of oxygen. So again, we're producing ozone. But if this NO, see up here, NO can also just react with ozone and go back to O2 and NO2. That's the ideal situation. At least getting back to NO2, which is not as bad. But if those NOs have a chance to react with a variety of different volatile organic compounds, those are producing new photochemical oxidants in the sky. So together, ozone and these other photochemical oxidants make up this. And then also, the particulates, the small, tiny particulates that come out of combustion processes, that plus photochemical smog, we get that hazy, gross stuff in the sky. So, okay, this could happen, and then if the weather patterns are good and the wind pushes it all away, it can at least get dispersed in a wide area, and that's better than having it concentrated above our cities. It's still bad for the environment in total, though, because that can travel across the world and affect other countries. But really dangerous things happen, and this is what happened with the Great London Smog, or things called thermal inversions. So this is when we have this warm layer at mid altitude, and it traps cold, dense air below, and the stuff that's trapped can't get out. So it's trapping the pollutants that accumulate beneath it. So what that looks like, actually, a better way to look at this is a diagram. So on a normal day, and you have good windy conditions, and the air pressure is such that it's not really high. So more lower air pressure-ish days, you get this warmer air down here near the surface, and you get cooler as you go above here. So it's the cooler air up here, cool and warmer. And yeah, we're producing a lot of this photochemical smog, but at least it can get pushed away. This also happens in basins too, more often, like places like Mexico City and Los Angeles, where they're kind of surrounded by higher altitude mountains. That is another spot where these things can get trapped. So what happens is, with certain weather conditions, instead, you've got this cool system, and then you produce all of this smoggy mixture, and it becomes relatively warm versus this cool. So it's trapped between cool and relatively warm. Or sorry, the warm is trapped between this cooler and cool. And this is a stagnant situation. There's not enough wind that's coming in here. Maybe you have a higher air pressure system. I took this from another article, and you get this trapped cold air. And within that trapped cold air, you have all our pollutants, which are now just being circulated amongst you and the citizens and are not getting pushed away. So this is what happened in London. You had a bad combination of a specific type of weather pattern and then just really, really high polluting coal power plants next to the city. It was this perfect storm to produce this really bad thermal inversion, and the city just sat in this dense smog, coal produced smog back then, and was so bad that it killed almost 12,000 people from respiratory issues, things like that, or maybe it combined with the flu. There's a lot of theories of how and why so many people died from that event. So that's really our jump about smog. Just wanting to point out that it still is a problem in the United States. And if you go to a big city like Los Angeles, you're going to see this hazy smog. Right now with the coronavirus, we're getting a lot of these type of situations. Again, this isn't from the coronavirus, but if you Google Los Angeles right now, you'll see all these photos of just crisp, clear skies you typically wouldn't see uh, depending on the weather patterns. So that is the smog issue. Now we're going to talk about a little bit about acid deposition. So those nitrogen oxides that get into the atmosphere and the sulfur oxides from other as primary pollutants can get into the atmosphere. And when they react with oxygen and water, they become secondary pollutants, actual acids, nitric acid and sulfuric acid. So these secondary pollutants will break down into nitrates and sulfates, and those can actually create this acid deposition process. They will actually break down to nitrates, sulfates in the water, and you'll get this deposition. So how does that work? It's actually pretty simple in terms of this diagram. This is kind of, we're not really saying what type of oxidants, but this could be photochemical oxidants that were produced through photochemical smog processes. But we have sulfur dioxide, some sort of nitrogen oxides, NO or NO2. They get oxidized into these compounds. Notice we had SO2 before. Now we have SO4. More oxygen is connected to the sulfur. Same thing over here. If this was NO2, we'd have NO3 over here as one example. And combined with hydrogen, these are acids. So sulfuric acid and nitric acid. When you mix those with water, they are going to give up their H pluses. And these H pluses are what are the really acidic components. These react as acids to our waterways, our crops, animals, buildings, etc. So this is how we get this acid rain or acid deposition. And the book notes this isn't as big of an issue as it used to be. We've done a lot better at containing a lot of these primary pollutants, at least. So we don't have these problems as bad as we used to, but we still do in specific areas. So some of those bad effects, well, you're lowering the pH of lake water, which is already a very balanced ecosystem. If you tweak the pH of systems, you're going to have a lot of effects on that system. I mean, our body in general, we have very specific systems in place to keep our pH close to 7. And we have things called buffers in our body. If a lake doesn't have any kind of buffer system, there's no way to keep the pH stable. And inside our body, if you change the pH, you'll actually break down proteins and enzymes that help our body function. So what this can do, this can start killing off species and decrease the diversity in those ecosystems. And it also mobilizes metals found in soils and releases these. So it mobilizes as in, instead of just solid metal kind of sitting there, you dissolve those with the acid in water, and now you have dissolved metals that can flow through the water system. So that's really bad as well. And then the other thing, maybe not so life altering, but it does damage structures. So statues in monuments and also ancient monuments. That's really sad too, to see these ancient monuments, maybe in Greece or something, that are getting deteriorated by acid rain, because those things aren't going to be around forever unless we help protect them. And this is because these are a lot of marble and limestone buildings specifically, and they contain a lot of calcium carbonate. Calcium carbonate comes from a lot of different mineral sources, but it reacts very easily with acids. It's essentially a weak base in water. So if you get an acidic solution of water, up against calcium carbonate, you're going to start reacting with it and break down those structures, basically dissolving this calcium carbonate into dissolved calcium and carbonate ions. So that's a big issue. Here is one of those ancient structures. So this is showing the effects of acid rain on these structures. It's pretty obvious. They become discolored, weathered looking, and a lot quicker than otherwise if it was just simply water and the wind kind of doing their typical effects on the rock surface. So that was key idea number 2. Really digging into photochemical smog, where it comes from, and then acid deposition. So the last part is, let's look at some approaches to control and prevent some of this outdoor pollution. Key idea number 3, examine various approaches to the control and prevention of outdoor air pollution. So prevention in general, so just trying to prevent the getting these pollutants into the air, and technology is a big thing, and then innovating your techniques. So this first picture is just one example, and it's electric. So electric buses. You see a lot of electric buses around, electric shuttles, electric cars, little things like that to decrease the amount of actual production of these pollutants into the air. But some more specific ways, so we still burn a lot of coal though. We still get a lot of electricity by coal. So there's one method is called fluidized bed combustion, which they get really small granules of the coal and they burn it next to calcium carbonate. And this is not, it has nothing to do with the calcium carbonate in general that we talked about, but it just so happens that calcium carbonate is also used in this process. And that calcium carbonate can actually absorb SO2, one of those primary pollutants. So that's one way to release those, decrease the amount of SO2 that gets in the atmosphere. Cars, I believe back in the 1970s, this became a requirement, mandate, a law that cars had to have these things called catalytic converters. Catalytic as in they need metal, they use precious metals, palladium is one, these metals that help convert NO2 or other nitrous oxides into less harmful gases, less harmful chemicals. So you put these on inside your combustion engines towards the outflow of your combustion products, and you can reduce NO2 conditions using catalytic converters. These last 3 are really for more particulate matter. These 2 are those gas compounds. These 3 we'll talk about in a little bit more in detail. These are used in maybe coal plants or other kind of power plants to help prevent particulates from getting into the atmosphere. The first one is kind of simple in the process. It's called a bag house filter. So you've got this housing and some bags, and it's called the bag house filter. So what happens here, you've got your dirty air coming through, and it's going to be pushed upward, and it's going to collect any particles that can't fit through this cloth or whatever this type of surface is, this filter bag, will get trapped in here, and you have your clean air outlet. And then to prevent this from getting clogged up, they have the shakers in here that shake out the particulates, and you collect those and get rid of those. So keeping particulates out of the air with these pretty crude but very effective method for keeping particulates out of the air. Second one is really interesting. This is called an electrostatic precipitator. So we have dirty air in here, and they're filled with particles, and they get, right away, they are going next to this really high voltage electrode. So that causes them to have a negative charge. They take on extra electrons. So we're basically we're making them anions, ionizing these pieces of material. And then we flow them through positively charged electrodes. So they stick really quickly to those. And then the clean air just goes out the other way. Really cool. And then how do we clean these? Well, we have to basically discharge these electrodes. So make them neutral again. And then this stuff can fall down here and collect, and we get rid of that as well. So that's a pretty cool system, the electrostatic precipitator. The last kind of mechanism we're going to talk about is what they call scrubbers. This we're using physical, just spraying water to grab the particles out of the air. So if you got your dirty air coming through, physical spray, well, the particles will get drugged down and grabbed by the water or scrubbed by this water and from this steam, and it'll get pushed down into this collection chamber. So this is now water with a whole bunch of particles. This is where the sludge is removed, and then we get that to a disposal unit. Then they are also recycling the water, so clean or cleanish, clean as possible, back into this. to scrub more water. So it's in a cycled system. Hopefully you're not losing too much water in the system, although you are going to have some lost from the sludge disposal, I'm assuming. Then you've kind of got a screen up here to make sure you keep any mist from going outside the system. You want to keep all the water in here, otherwise we'll lose the water and have to just use a lot of water instead of reuse that water. And then the cleaner exit through those stacks. So that's the last type of, then these are just three. These are just three examples of showing how we get particulates out of the air. And then just a few examples of showing how we try to prevent primary pollutants from getting into the air. All right, so that is the part two. I'm going to go back to the beginning here. We have the smog, acid, and then prevention. And that's the last part, or the next two of this section. The last two will be talking about ozone. And remember, we want ozone. That's the other part of it. We're going to talk about how ozone is good, and there's actually a problem with depleting it. And then we're going to talk about indoor air pollution. We haven't really talked a whole lot about indoor air pollution yet. So we'll talk about those in the next video. And I'll be sure to post these up on the course website. See you guys then.